Hello friends, I welcome you in lecture number 12 on relations. In this lecture we will discuss this problem on checking the properties of given relation on a given set. So first we understand what is this problem. Let capital R be the relation on this set of integers defined as R equal to ordered pair AB such that A plus B is less than or equal to 3. Determine whether R is reflexive, symmetric, transitive and antisymmetric. So first we understand that two integers A and B are related to each other if their addition is less than or equal to 3. The ordered pairs AB in the given relation must satisfy this condition. For example, if I take A equal to 1 and B equal to 2, then A plus B equal to 3. Therefore, order pair 1, 2 is in this relation. Similarly, we can have 0, 2 also. Addition of 0 and 2 is equal to 2, which is less than 3. We may have minus 1, 2 also. If we add minus 1 and 2, we will have 1, which is less than 3. So in this relation we have this type of ordered pairs such that addition of these two components is 3 or less than 3. Now we have to check all these properties for given relation. First we have to check whether relation is reflexive or not. So for reflexive relation we require this condition. If we take any integer, then relation is reflexive if that integer is related to itself, that is A, A belongs to R for every A in the set of integers. Now if this is true, then we must have this condition satisfied, that is A plus B less than or equal to 3. Here both the components are equal, so A belongs to R if A plus A is less than or equal to 3. This is true if 2 times A is less than or equal to 3, and this is true if A is less than or equal to 3 by 2. So from this we can have the idea that we have this condition for relation to be reflexive. If our integer is smaller than 3 by 2, that is 1.5, then only this condition will be satisfied. So if I consider any integer which is bigger than 1.5, for example if I consider A equal to 2, then we know that 2 plus 2 is 4, which is greater than 3. So 2, 2 is not in given relation because this addition is not less than or equal to 3. Similarly, if we take A equal to 3, 4, 5 and so on, if we take any integer which is greater than 1.5, then this condition is not satisfied. And for relation to be reflexive, we must have order pair A belongs to R for every A in the given set. Here given set is integer. So this relation is not reflexive because we have particular integer for which that condition is not satisfied. So how to write this? So we can simply write that for integer 2, for 2 belongs to Z, we can say that 2 plus 2 is equal to 4, which is not less than or equal to 3, or it is greater than 3. So because 2 plus 2 is not less than or equal to 3, 2, 2 is not in the given relation, and therefore R is not reflexive. If R is reflexive, then we must have order pair A belongs to R for every integer A, but that condition is not satisfied here, and therefore this relation is not reflexive. Now we can check the symmetry property. Second condition we have to check is of symmetry. So for symmetry, we should check that whenever AB belongs to R, we must have BA belongs to R. If AB belongs to R implies BA belongs to R, then relation is symmetric. Now AB belongs to R if A plus B is less than or equal to 3, and BA belongs to R if B plus A less than or equal to 3. And we know that addition operation is commutative, so if A plus B is less than or equal to 3, we can say that B plus A is also less than or equal to 3. Therefore this relation is symmetric. So we should write that for any AB belongs to Z, if we take AB belongs to R, for any AB belongs to Z, AB belongs to R implies A plus B is less than or equal to 3, and because addition operation is commutative, we can write A plus B equal to B plus A, and this implies order pair BA belongs to R. So whenever AB belongs to R, we have BA belongs to R for any two integers A and B. Therefore this relation is symmetric. If our relation is satisfying particular property, then we have to prove that property for arbitrary elements in a given set, and if relation does not satisfy any particular property, then we have to give counter example. We have to find out particular element in a given set for which that property is not satisfied. Here relation is not reflexive, so I have written this particular integer 2 for which 2 is not in R. Next property is transitive property. So for transitive property, we have to check that whenever AB belongs to R, that is A related to B, and BC belongs to R, we must have AC belongs to R. If AB belongs to R and BC belongs to R, then we should prove that AC belongs to R for relation to be transitive. So suppose this is satisfied, that we have obtained two order pairs for which AB belongs to R and BC belongs to R. Then first we try to prove whether AC belongs to R or not. Now AB belongs to R implies A plus B less than or equal to 3, and BC belongs to R implies B plus C less than or equal to 3. Now from this 2, can we say that A plus C is also less than or equal to 3? If this is true, then relation is transitive. That is, if A plus B less than or equal to 3 and B plus C is less than or equal to 3, is it true that A plus C is also less than or equal to 3? So common sense says that this might not be true. We can have AB and BC such that A plus B less than or equal to 3 and B plus C less than or equal to 3, but A plus C may not be less than or equal to 3. So we are having doubt that this property might not be true. So whenever we have doubt, we have to find out particular integers ABC satisfying these properties, and we have to check for particular elements. If we can obtain ABC such that AB belongs to R and BC belongs to R, but AC is not in R, then that property is not true. Now we have to decide ABC in such a way that these two are equal. Second component of order pair AB is equal to first component of order pair BC. So you can see that if I consider 2, 1, then 2, 1 belongs to R, because 2 plus 1 is equal to 3, and here I must consider 1. So 2, 1 belongs to R, and we can see that 1, 2 is also in R, because 1 plus 2 equal to 3. Therefore this is also in given relation. So it is clear that 2 comma 1 belongs to R and 1 comma 2 belongs to R. Now if relation is transitive, then we must have 2 comma 2 belongs to R. So now 2 comma 2 belongs to R if 2 plus 2 is less than or equal to 3, but we know that 2 plus 2 is not less than or equal to 3. 2 plus 2 is equal to 4 and it is greater than 3. So 2 comma 2 cannot be in R. So here we have obtained two ordered pairs such that 2 1 belongs to R and 1 2 belongs to R, but 2 comma 2 is not in R because 2 plus 2 is not less than or equal to 3, and therefore this relation is not transitive. So whenever your relation is not satisfying particular property, you have to give counter example, and here we have obtained this counter example. So this means relation R is not transitive. Next property is antisymmetry. So for antisymmetry, we have to prove that whenever AB belongs to R and BA belongs to R, then A and B must be equal. If AB belongs to R and BA belongs to R implies A equal to B, then relation is antisymmetric. In other words, if A and B are different, then this cannot be true. If A and B are different, then either AB belongs to R or BA belongs to R. Both cannot be related to itself if A and B are different. So suppose we try to prove this first. Suppose AB belongs to R and BA belongs to R. We assume that AB belongs to R and BA belongs to R, and we try to prove that whether we obtain A equal to B or not. AB belongs to R implies A plus B less than or equal to 3, and BA belongs to R implies B plus A less than or equal to 3. But from this we cannot say that A and B are always equal. So there is a chance that relation is not antisymmetric, and for that we have to find out two different integers A and B such that AB belongs to R and BA belongs to R. And if we have noticed in third property, we have already obtained these two integers. For 1 2 belongs to Z, 1 2 belongs to R and 2 1 belongs to R. 1 2 and 2 1 are present in our relation, but 1 and 2 are different. So this shows that given relation is not antisymmetric. So we can write that for 1 2 belongs to Z, 1 comma 2 belongs to R, and 2 comma 1 belongs to R, but 1 and 2 are different or distinct. Therefore relation R is not antisymmetric. So in this way we can check whether given relation satisfies particular properties or not. First try to prove the property using the definition. If you are not able to prove that property, then you may have doubt that that property might not be true. So in that case, think for particular counter example. So whenever you want to prove the property, you have to prove for arbitrary elements, and if you disprove the property, you must give counter example. You must give particular order pair which does not satisfy that particular property. So this is all about this session. I hope you like it. Thanks for watching.